I'm Matthew.
And I'm Sophie.
And we're from the University of Cambridge in the UK.
So in the first part of this lesson on structural hazards, we learned that earthquakes don't kill people, but collapsed buildings and their contents do. We built models of buildings and we tested them on a mini shake table. In this lesson, you're also going to get to build some more building models and test out their strength.
Now this may seem a bit unrelated, but have you ever been on a swing? And if you've been on a swing, how do you make yourself go higher and higher? And if you've got a friend, how do they make you get even higher? Take a few minutes to think about the swing questions, but also to go through these 3 terms on the board, to think about them and discuss them with your teacher to make sure you understand them. So that's frequency, natural frequency, and resonance. We'll come back to you shortly.
Welcome back. Now that you've had a chance to think about how to swing and learnt about some new terminologies, let's go and play in a park.
Hi everyone.
We've come to the park to demonstrate resonance.
If I push Matthew when he's at the furthest extent of swinging, then I'll also be pushing him at the natural frequency of the system. This will amplify the effect of his swinging and allow him to go higher. This effect is called resonance. If I stop pushing him, then I won't be pushing at the natural frequency of the system, and eventually he'll stop swinging.
Hello, so we're back in the class again. So let's explain why learning how to swing on a swing is actually relevant to this topic. So when you're swinging on a swing, you're moving at the natural frequency of the system. And when your friend pushes you on the swing, they're pushing you at the natural frequency of the system. And when they push you at the biggest extent of when you're swinging at the biggest extent of the arc, this causes an effect called resonance, which increases the amplitude you're swinging, so you go higher and higher. If they didn't push you at this natural frequency, this wouldn't happen and you wouldn't be able to swing higher.
Can you think of other examples like the swing that demonstrate the concepts of frequency, natural frequency, and resonance? We've thought of a few, such as a cello or another string instrument when it plays a note, or parts in a car that vibrate when you're going at a certain speed on the road. And also a pendulum.
So you might ask why these concepts are relevant to this topic of natural hazards. Well, the thing is, when an earthquake happens, this effect of resonance happens to buildings. So when earthquake vibrations happen, and if they are at the same frequency as the natural frequency of a building, this causes the building to resonate, and the amplitude of the wave movements of the building will increase, and this could eventually cause it to fall down.
You are now going to place a wooden block on a shake table and see how the wooden block responds to different frequencies of vibration. The wooden block represents a building and the shake table represents an earthquake. Now, do you remember what a shake table is? Don't worry, because we're going to go through it now. A shake table is a device that earthquake engineers and technicians use to test out models to see if they'll be able to withstand the shaking like an earthquake. Now, all the different components are down here. We have the base, which is attached to the upper layer by elastic bands like this. And on the base, there are various holders with small marbles in, so that the top level can move about. Now this here is a motor that can spin around and it's powered by a battery. And when you connect that up, it's also connected to a potentiometer. When you turn the potentiometer around, it can change the different frequencies. So it can be a low frequency or a high frequency and cycle through them. And that will change how much and how quickly the shake table is shaking.
So a shake table is really useful because it allows us to investigate the effect of ground motion on different structures. And as Matt said, with the potentiometer as well, it's very useful because you can cycle through different frequencies and see what the effect of different levels of shaking are on ground motion and therefore structures. Before you do anything, try and predict the following. What would happen to the wooden block at low frequencies? Is there a frequency at which the block shakes excessively and falls? And what would happen if you go through this frequency quickly? Would the block fall at all?
After you've made these predictions, try out your model on the shake table and see if you were correct. We'll come back to you in a few minutes and see how you got on. Welcome back. How did you get on? We're now going to test the wooden block on the shape table.
What do you think is going to happen?
I predict that, like in the first lesson, our model shook a lot at low frequencies because that must have been its natural frequency, but when it got to higher frequencies, it didn't shake as much.
Okay, so should we test it and see what happens?
Yeah, let's go.
Okay. Right. So we're just connecting it up now.
Let's start with the low frequencies. It's shaking a bit.
Oh wow, it's really going.
Well, I think that was fairly clear. We got it wrong again.
We should really start making better predictions.
Yes, I bet you guys are much better at doing this than we are.
So notice that when the frequency of the shaking matches the natural frequency of the block, it shakes a lot and can fall over. This is called resonance. But when the natural frequency of the block is not matched by the frequency of the shaking, it only shakes a little bit and stands tall. So structural engineers use a variety of techniques to try and reduce resonance in buildings during earthquakes. One of these techniques is known as base isolation, and it's where structural engineers use devices that look a little bit like wheels in the base of the building, which directly stop any of the transfer of energy from the base of the building to the rest of it.
It's kind of like shock absorbers in cars that cushion their occupants from having a bumpy ride. Another thing that you can put into buildings to dissipate the oscillation and reduce the seismic shaking are dissipators. These dissipators can be put at various points in the building, and it means that the different parts of the building move relative to each other, which therefore dissipates the seismic energy and the frictional energy, so it doesn't shake as much. Now take a minute to briefly discuss in groups the different ways that you think that you could make a building more earthquake proof, that it could withstand greater earthquake loads.
So while you discuss this in groups, also think about ways that you could modify your models to withstand higher levels of shaking, and then modify and test your models on the shape table. We'll be back soon to talk about how you got on.
Welcome back. Now you've had a chance to discuss the various ways that you can make a building stronger and more able to withstand earthquakes, let's have a go ourselves by building our own walls and seeing what happens when we shake the base of it.
So here's the materials that you'll need for assembling your wall. So we've got craft sticks, which have a hole drilled in either end, and you can put a screw through all of these holes, and you've got a washer and a nut, which you'll be able to attach different craft sticks to each other with. Now, here's our model that we made earlier, and as you can see, we've used the materials that we've just explained to you to be able to construct a lattice kind of system to make the wall. And at the bottom here, we've got the base, which if I just turn it around to the back, you can see has a place to hold at the back of the wall. So you can attach the craft sticks and the screws to the base because they've got holes drilled in them as well. So your teacher will help you construct this if you're struggling a little bit.
And make sure when you're putting the screws in that you screw them tightly enough that they don't fall apart, but not too tightly so that it can still move around. Once you've assembled your wall, have a think about these two questions that we've got written up on the board. So what holds this wall up? And secondly, predict what will happen if you push on the base of the wall side to side.
So after you've had a chance to think about what might happen when you push the wall back and forth, get one of you to gently push the wall back and forth by using the bit round the back of the wall, which we showed you earlier. So just hold on to this bit at the base here and just push it gently back and forth. And then think about whether your predictions are correct, and think about what the weakest parts of the wall are.
We'll come back to you shortly and see how you got on.
Welcome back. How did you do? What do you think holds this wall up? The interaction of the vertical and the horizontal elements helps to keep this wall together and to withstand the load of the structure. Let's see what happens when we push this model side to side fast.
What do you think is going to happen, Sophie?
Well, I would think that the floors won't hold up particularly well on this structure, but should we have a go and see what happens?
Yeah, let's have a go.
Okay, I'm just going to push it from side to side very gently to start off with, and then a little bit more strongly, so you can do this yourself. Oh, okay.
As you can see, only the first floor collapsed. The floors above it didn't at all. That was because the first floor was too weak to transfer the horizontal shaking up to the other floors above it. There are some real examples of how this damage can be done in real buildings, such as buildings with hollow first floors, such as garages, and they collapse first and don't transfer the horizontal shaking up to the higher floors.
So let's think about ways in which you can modify your wall structures to withstand this better and to make sure that the first floor maybe doesn't collapse. So we've got some materials that we can show you as some examples. So you can get as creative as you want, use any materials that you've got in your classroom, but you can use more of the craft sticks, the screws, and we've got some string here, some cardboard, paper clips, paper clamps. Before you do anything, predict what you think is going to happen once you've made the modifications to your structure, and then test it out by doing the same thing by moving it from side to side gently to start off with and then more strongly, and then think about how your predictions were, what happened to your structure, and did the same thing occur? Did the first floor collapse?
When you modify your wall, make sure that you're trying to transfer the horizontal shaking up from the bottom to the top. Off you go and see how you get on.
Welcome back. How did you do? Were you able to modify your wall to make sure that it didn't fall down? But you've probably guessed that there are lots of different ways that you could modify a wall in order to make it stronger. This is our wall, and we've added various things to it to make it stronger, and Matthew's going to go through some real life examples of where you can see these kind of modifications that we've made, and I'll kind of point to where they are on our wall.
So, there are three main ways that earthquake engineers can use to strengthen these buildings and make sure that the force, the horizontal force which shakes back and forth, can be transferred from the bottom to the top of the building. Firstly, we've got the diagonal braces, which are made out of these craft sticks, and they strengthen the building. Then we have the shear walls made out of this cardboard, and they help transfer the horizontal shaking up the building. Often these walls aren't actually load bearing at all, they are only used to transfer this energy. Then we have rigid connections, which keep all the parts of the building connected to each other so they don't move relative to each other, and that again transfers the horizontal force up.
So should we have a go at testing out some of the modifications that we've made?
Yeah, let's go.
Okay, so start off by shaking it gently to start off with and then more strongly as we did before. Okay, that didn't take a lot, but as we can see, the first floor hasn't collapsed as it did before, but the top floor has collapsed. Can you think of any reasons why that might be, Matthew?
Well, I guess because we've put all of the diagonal bracings and the shear walls and everything else on the lower layers, that means that we can transfer the horizontal shaking up the building, but then we haven't put anything on the top floors, so that's why the top floors have collapsed.
Okay, so actually what you could do is add more of these modifications to the top floor to make sure that the whole building was earthquake proof.
Yeah, that would work.
Okay, cool. So you guys could have a go at doing this in your class if you want to see if you can make the rest of your structure not non-collapsible, basically. So yeah, cool. So in conclusion, we learned that earthquakes don't kill people, but collapsed buildings and their contents do. Structural engineers use a variety of techniques to try and reduce resonance in earthquake-prone buildings, and we can add structural elements to buildings to ensure that they are strengthened. And actually, these modifications result in stronger buildings. These elements provide a path for the transfer of horizontal force throughout the building, as we've seen with our structures. Before we say goodbye, we'd like to invite you to reflect on the following questions.
What are the similarities and differences between the model wall and actual walls in real life? How can you modify your wall to be more like a real wall that may undergo an earthquake?
Can you think of any buildings in your local area that could benefit from some of the structural elements that we've modified our buildings with today?
We hope you've learnt a lot today by building and testing your models on the Shaky table. Remember that buildings can withstand earthquakes if they're built according to the earthquake regulations that are appropriate to your area. We hope you've enjoyed the lesson.
Thank you and goodbye from us.
Goodbye. Hello, I'm Matthew.
And I'm Sophie, and we're from the University of Cambridge in the United Kingdom. Thank you for checking out this video. This is the second part of a two-part lesson on structural hazards, designed to follow the part one. It should take approximately just under 1 hour to complete this lesson.
The learning objectives for this lesson are to introduce the concepts of natural frequency and resonance and how these are relevant to earthquake hazards. We also want the children to learn about how buildings can be changed in different ways and altered so that they can withstand earthquakes much better.
In the first activity, we'd like you to go through some of the more theoretical concepts that we've gone through in previous lessons, like frequency, natural frequency, resonance, and amplitude. If you've got a nearby swing near you that you think would be a good way to engage the students, feel free to take them there. And think of some real-life examples of resonance, maybe from your local area, that could, again, engage the students more fully.
The next activity involves a wooden block on a Shaky table. If you're unsure on how to construct a Shaky table, which you should have constructed before the lesson starts, then all the instructions are in the reference materials for this video. We want the children to investigate what happens at different frequencies to the wooden block, so test out those different frequencies by using the Shaky table. And if the children are unsure with how the Shaky table works, then make sure you go through the theory of the Shaky table before the lesson starts.
In the third activity, we ask students to modify their wooden blocks in order to withstand the shaking more effectively. So you can use some of the materials that you can use: styrofoam, string, paper clips, paper clamps, anything that you've got in your classroom really. Just be creative, anything you've got to hand. And as ever, because it's a practical lesson, make sure that the children are being safe with the materials, and if they need a hand with anything, just give them a hand.
To prepare for the wall model activity that we have here, you can build this wall model before the lesson, or you can get the children to help you in the lesson itself so they feel more involved. To build the wall, you can follow the instructions that are in the reference material to this video. All these components are readily available throughout the world, and if you need to, you'll have to cut them down to the right size and drill some holes in as well.
So one important point to remember is not to screw the screws too tightly, because this will stop the wall model from falling down or being able to respond to any of the motion that you put it under. But make sure that they're screwed tightly enough so that it holds together. And then think about the fact that you could have one wall model that you use as a demonstration in front of the class, or you could have several wall models that you hand out to different groups and they have a go themselves. It's really up to you and what you think will suit your class better. And make sure you have enough materials for your class. The materials that you'll need are craft sticks, screws, and the base for the wall model, which we've explained in the segment already. But yeah, these are easily obtainable pretty much anywhere in the world.
In the final discussion, feel free to add any more questions that you feel are appropriate about the strengths and weaknesses of this wall model and how it applies to real walls and how they are affected by earthquakes in the real world. Good luck and thanks very much for choosing to watch this video.
Goodbye.
Bye.